Hello, students. Today we are going to study number sequences and patterns. It is part of IGCSE and other higher secondary school diplomas curriculum. For IGCSE students, there's been a gradual change in the topic number sequences and patterns. Earlier, some types of sequences, like quadratic sequences and exponential sequences, were not included in the exams, but now it is officially made part of the syllabus. It's not too difficult, and we will learn everything step by step. We'll also do past papers to prepare you for your upcoming exams. You have to just maintain a bit of stamina and remain focused. Okay. In sequences, there is no much heavy math involved, but there is a lot to understand. Stay sharp. The first and most important thing to understand is that this is not one chapter. It's actually two separate chapters. Number sequences is one, and patterns is another. So we'll start with sequences. So let's begin with number sequences. The first type of sequence in our syllabus is called an arithmetic sequence. In arithmetic sequences, each term changes by the same fixed number every time. For example, 2, 6, 10, 14. Each term is increasing by 4, so the next term in the sequence will be 14 plus 4 equals 18. And after that, 18 plus 4 equals 22. Similarly, you could also have sequences where each term decreases by the same amount. In this example, we have a difference of -3. Therefore, as we can see, the next term in the sequence will be 20. And if you subtract 3 from 20, we will get 17. The key is that the difference between neighboring terms must always be constant. Either same value is added or subtracted. So, arithmetic sequences are those sequences where the same amount is added or subtracted each time. Sequences where we multiply or divide by a constant number are called geometric sequences. But that is not covered in O-level syllabus. Therefore, geometric sequences will not be tested in O-levels exams. We will only deal with arithmetic sequences here. Till now, we have seen two arithmetic sequences in which we found out the fifth and sixth terms by adding or subtracting the fixed number in the sequence. However, if someone tells you to find the nth term, then we have a formula for an arithmetic sequence nth term. And the formula for the nth term of an arithmetic sequence is an equals a plus d whole multiplied by n minus 1. Don't worry, if you don't know what an means, I'll explain that to you. So the n-term formula is an equals a plus d whole multiplied by n minus 1. Let's first understand what each symbol represents. A is the first term of the sequence. For example, in the first sequence, a equals 2. In second sequence, a equals 32. So a is always the first term. Clear? Great. Next, D is called the common difference. Remember, we just learned that arithmetic sequence has same number added or subtracted each time to get the next term. This amount by which the sequence increases or decreases every time is called the common difference and denoted by D. But how do we find the common difference? Pick any two neighboring terms and subtract the previous term from the next one. For example, in the first sequence, taking any two neighboring terms like 14 and 10, so 14 minus 10 equals plus 4. Similarly, let's find the common term in the second sequence. we pick two neighboring terms, 29 and 26. And 26 minus 29 equals minus 3. That's the common difference. If the sequence is increasing in numbers or moving upward, D will be positive, as we can see in our first example. And if the sequence is decreasing, say 32, 29, 26, then the common difference is negative. Always use the formula next term minus previous term. Don't just rely on intuition or memory, especially when the numbers are negative. There, you might get confused if you don't use the formula of next term minus previous term. So far, we've learned A equals first term and D equals common difference. Now let's address a big confusion. What is n and what is nth term and what is difference between them? Let's look at this number here, 10. Which position is it in? It is at position number 3, right? Or we can say it's the third term of the sequence. So here, n equals 3, and an, or a3, equals 10. In this case, an is called a3, as n is replaced by 3. The position is given by n, and the value written at that position is an. Let's look at another number. For example, if the fourth term is 23, then n equals 4, and an, or a4, equals 23. So remember, n tells the position of the term, an tells what value is written there. If n equals 3, that means the third position. At that position, n equals 3, the value, a3, is 26. Now we know that in formula of an for arithmetic sequences, an equals a plus d whole multiplied by n minus 1. Let's recap what each term means in the formula. An is what's written at the location number n, while n is the location of term. A is first term of the sequence, and D equals common difference of two neighboring terms of the arithmetic sequence. Okay, now let's do one question which will cover all the questions that examiners can ask in arithmetic sequences. The sequence is 5, 8, 11, 14, and so on. The question asks, write the next two terms. First of all, check if it's arithmetic sequence. Well, how do you check that? As already explained, we find the difference of two adjacent terms and it should be same. So let's do it. Here it is 8 minus 5 equals plus 3, 11 minus 8 is plus 3, and 14 minus 11 equals plus 3. Therefore, it is arithmetic sequence, as common difference is same. I hope you can write the next two terms now. As the difference is plus 3, so we add it to the previous term to get the next term. So, 14 plus 3 equals 17, and 17 plus 3 equals 20. The next part of the question is to write an expression in terms of n for the nth term. First of all, expression means equation. So the question is asking to write the equation of an in terms of n. That means our answer must include n as the generic equation of an is an equals a plus d whole multiplied by n minus 1. In the equation, a is the first term of the sequence, which is 5 in our case. The term d is the common difference of two adjacent terms of the sequence and can be calculated by the formula next term minus previous term. We have already calculated it while checking for the sequence. Therefore, d equals plus 3. Substituting a and d in the equation, we get an equals 5 plus 3 whole multiplied by n minus 1. Simplifying the equation, we get 5 plus 3, n minus 3, and finally 3n plus 2. That's our general formula for this sequence for any term. What does this mean? It means by using this formula, we can calculate n's term at position n. By inserting the position number n in the formula, we can find out the value of an, or nth term, for that position. For example, to find the third term, a3 equals 3 times 3 plus 2, which equals 11. So as you can see, that in our sequence also, we have 11 at position number 3. So an tells us what value is written at any given position n. In the next question, if we want the 40th term, we don't need to write 40 numbers manually in the sequence. This might be correct, but is very time-consuming. Just plug n equals 40 into the formula. Here, an also become a40 as n is replaced by 40 in the formula. Therefore, a40 equals 3 times 40 plus 2, which equals 122. This means that if we go to the 40th term, we will find the value 122 over there. So, n equals 40 means the 40th position, and a40, which equals 122, is the value written at the position 40. In question 4, we are given that the value of nth term of sequence is 65. Find n. This means that if we keep on writing the sequence, we will have a term whose value is 65. We know the value, but we don't know the position of the value 65. I hope by now you know the position of sequence is n, and the value at that position is nth term. To find the position, or in other words, the value of n, we will use the an formula for the sequence, which is an equals 3n plus 2. Here, an is 65, and we have to find the value of n. Therefore, we will plug in the values in the equation, and we get 65 equals 3n plus 2. Solving it gives us 3n equals 63, and n equals 21. There we have it. The value 65 is present at position 21. Hope this further clarifies difference of n and an. Okay, next question. Given that the kth term of a sequence is 83, find k. This means somewhere in the sequence, the value 83 appears at a specific position. We have to find which position that is. We know an equals 3n plus 2 is the generic formula for our arithmetic sequence. Here, you may get confused with the letter k instead of n. Remember, the generic formula is in terms of n. If we want to find k and kth term, just replace the letter n with k. Now, instead of n, the position of term will be k, and the value present at position k will be called kth term instead of nth term. Okay, since we are being asked for k, therefore we replace n with the letter k in the generic formula, and it becomes ak equals 3k plus 2. Now, is 83 the position number or the value written at that specific position? Well, as the question says, it is the value at kth position, so don't confuse it with the k, which is the position. So we put 83 in the equation as the kth term value, or ak. This gives us 83 equals 3k plus 2. By solving, we get 81 equals 3k, and finally, k equals 27. So the value 83 is at the 27th position in the sequence. Therefore, the value of k is 27. Okay, we have come a long way. Let's revise what we have studied. There are 4 sorts of sequences which we have to cover in O-level syllabus, and the first is arithmetic sequence. If same value is added or subtracted from the term to get the next term, then it is arithmetic sequence. The number which is added or subtracted is called common difference, denoted by the letter D. The letter N shows the position of the term, and nth term tells what is written at the position N. To get the nth term formula of arithmetic sequence, we put in the value of A, which is the first term of the sequence, and D, the common difference of the sequence. If the sequence is descending, then the common difference is in minus, and we do take negative sign while putting the value of D in the equation. After plugging the value of A and D, we get nth term formula in terms of n. Sometimes the examiner switches the questions. He may ask the value of nth term and give you the position of the term, which is n. And sometime he may give you the value of n, which is position of term, and ask for the value present at that position, which is the nth term. Sometime the examiner replaces the alphabet n with other alphabet, like in our example, where we had to find the value of k, which is the position of term, and normally denoted by n. If a student understands these 5 main steps, there's no question in arithmetic sequences that can go beyond them in exams. Okay, little attention required now. Whenever we look at a sequence question, the very first thing we'll ask is, what type is it? Is it arithmetic? And I am sure by now you know how to identify arithmetic series. Yes, same value will be added or subtracted between 2 neighboring terms. If it is not arithmetic series, then it must belong to any of 3 categories. Remember all 3: square numbers, cube numbers, and triangular numbers. Now, this may be confusing to understand the 3 sequences now, but in just a couple of minutes you'll find it easy. And this is the core concept of the entire chapter. Once we're done with this, the rest will be simple. Okay, you need to memorize these 3 types of numbers: square numbers, cube numbers, and triangular numbers. Square numbers are 1, 4, 9, 16, 25, 36, 64, 81, and 100, and so on. You should at least know the first 4 by heart, so that you can instantly recognize when they appear, because identification is key in such questions. Cube numbers are 1, 8, 27, 64, 125, 216, and so on. Again, the first 4 are crucial to memorize because recognition depends on them. All right, now triangular numbers. This would be new for you. They are 1, 3, 6, 10, and so on. There are 2 ways to understand their pattern. Let me explain. Triangular numbers basically mean the number of balls or dots needed to form a triangle. For example, if you've ever seen snooker balls, you might have noticed that if you want to make the smallest triangle with balls, you'll need at least 3 balls. You can't make a triangle with fewer in this case. Next time, when can you form another triangle? When you have 6 balls. You can't make triangle with 4 or 5 balls. And the next bigger triangle can be made up from 10 balls. That's why they are called triangular numbers, because they can form triangles. Now, there's another very important pattern inside them. You must know how to detect it. From 1 to 3, how much are we adding? +2. From 3 to 6, we are adding plus 3. From 6 to 10, how much? Plus 4. The next one will add plus 5 to give us the number 15. Similarly, the next term will be 21 after adding 6. Got it? So you need to remember these three sequences: square numbers, cube numbers, and triangular numbers. By the way, the logic for square numbers is similar. You need 4 balls to make one square, then 9 balls for the next, then 16, and so on. You can't form a square with other numbers. All right, up to here, clear? Now remember, square numbers are 1, 4, 9, 16, 36, and so on. Cube numbers are 1, 8, 27, 64, 125, and so on. And triangular numbers are 1, 3, 6, 10, 15, and so on. These are the essential sequences. Now, what will be the nth term of square numbers? N square. What about cube numbers? It's n cubed. Simple. So, for square sequence, we use the formula for nth term as n square, and for cube sequence, the formula is n cubed. We can identify them easily. Coming to triangular numbers, remember this formula: 1 divided by 2 multiplied by n whole multiplied by n plus 1. That's your triangular number formula. So whenever you see a sequence like 1, 3, 6, 10, you'll know its nth term is 1 divided by 2 multiplied by n whole multiplied by n plus 1. But there's one limitation. These nth term formulas only work if the first term of the sequence is 1. If the sequence doesn't start from 1, these formulas won't directly apply. You'll have to adjust them. And that's what we are going to cover today, so stay attentive. So, for square, cube, and triangular sequences, you must first recognize which family the sequence belongs to. When you do past paper questions, you'll realize that in 90% of the cases, when a sequence didn't make sense to you before, it actually belonged to one of these families. Now remember, square numbers are 1, 4, 9, 16, 36, and so on. Cube numbers are 1, 8, 27, 64, 125, and so on. And triangular numbers are 1, 3, 6, 10, 15, and so on. And their nth term formulas are n squared, n cubed, and 1 divided by 2 multiplied by n whole multiplied by n plus 1. Memorize them for exams. Okay, as we have discussed, these formulas only work if the sequence starts from 1. But if it starts before or after 1, that's where shift comes in. It may seem a bit complex, but the actual logic is simple, just a one-step adjustment. Remember, if the sequence doesn't start from 1 and it's after 1, we call that a forward shift. If it's before 1, meaning it starts from 0, we call that a backward shift. So, if the sequence starts after skipping 1, for example from 4, 9, 16, it's a forward shift. If it starts from 0, it's a backward shift. In forward shift, if one term is skipped, then replace n with n plus 1. If 2 terms are skipped, then replace n with n plus 2. Just hold this concept, and we will discuss it in a minute, and it will make sense. In backward shift, when the sequence starts with 0, replace n with n minus 1. Here is an example. Write the nth term of the sequence. By looking at the sequence, the first thing, you must always ask whether the sequence is arithmetic or not. And How you check for the sequence to be arithmetic? You check if the difference between adjacent terms is same, which we know as common difference, denoted by D. Here, as you can see, it is not same. Therefore, it's not arithmetic sequence. Therefore, it must belong to one of these families, square, cube, or triangular. For example, these are square numbers, right? Yes. But are they the original square numbers? Well, the original one starts from 1, and in that case, its nth term would simply have been n squared. But as the sequence has skipped the first term, 1, therefore, it's a forward shift. Hence, for nth term, we write n plus 1 whole squared instead of n squared. If it was shifted by 2 terms, then we would write n plus 2 whole squared. Let's solve another example. Write down the nth term of the sequence 8, 27, 64, 125. The first question should be, is it arithmetic? As the difference between two adjacent terms is not same each time, it belongs to square, cube, or triangular numbers. As we have memorized the first terms of the sequence, therefore we can figure it out these are cube numbers. Okay, they are cube numbers, but they are not the original cube numbers as they are not starting from 1. Original cube number would have been 1, 8, 27, 64, and its nth term would have been n cubed. But since the sequence is shifted by 1 term, we will replace n by n plus 1, and the answer to the nth term will be n plus 1 whole cubed. If you remember the sequences, then by just looking at the sequence, you can answer the question verbally, without working on the paper. Such type of questions are very easy, and they're just 1-mark questions because no working is required for it. Let's do another example. Write down the nth term of the sequence. First question, is it arithmetic? Check whether the difference between consecutive terms is the same each time. The answer is no. Therefore, it belongs to either square, cube, or triangular sequence. By looking at it and recalling the first few terms of the 3 sequences we have memorized, we know they are cube numbers. But they are not starting from 1, therefore they are shifted cube numbers. Now to see how many terms they have been shifted, we write the original cube numbers, which is 1, 8, 27, 64, 125. By comparing both, we can see that the given numbers are shifted by 2 terms. The original nth term would have been n cubed, but since it's shifted, you'll replace n accordingly with n plus 2. So the answer will become n plus 2 whole cubed. Got it? Does that make better sense now? In the exam, it's up to you whether to show the working or not. Technically, no working is required. Now, write down the nth term of the sequence 0, 1, 8, 27, 64. First, recognize which family it belongs to. Cube numbers, right? Good. The original cube numbers are 1, 8, 27, 64, and so on. But our sequence is starting from 0, so this is a shifting towards left. It's called a backward shift. Backward shift means you move before the original first term. It can only go 1 step backward from 1 to 0. So instead of n, you'll put n minus 1. Originally, it was n cubed. Now it becomes n minus 1 whole cubed. All right, now I want you to first revise it so that it gets memorized thoroughly. If any sequence is not arithmetic sequence, then it belongs to square, cube, or triangular families. You must memorize the first 4 terms and their nth term formulas. For 1, 4, 9, 16, it is n squared. For 1, 8, 27, 64, the formula is n cubed. And for 1, 3, 6, 10, it's 1 by 2 times n whole multiplied by n plus 1. If the sequence start from 1, then these nth term formulas work perfectly. Just write them directly in the exam. If they don't start from 1, that means a shift has occurred. A forward shift happens when your sequence starts after skipping the first few terms. Then, instead of n, write n plus 1 or n plus 2 in the nth term formula, depending on how many places were skipped. In backward shift, if the sequence starts before the first term, meaning 0, then replace n with n minus 1.
All right, let's revise. In the first example, we recognized square numbers, as the sequence started from 4 instead of 1, so one term was skipped. Hence, we used n plus 1 instead of n. In the second case, we recognized the sequence as cube numbers. Again, instead of 1, it started from 8, so again one term skipped, therefore we replaced n with n plus 1. In the next one, 2 terms were skipped, so we replaced n with n plus 2. In this sequence, there was a backward shift. It started from 0 instead of 1. So n was replaced with n minus 1, giving the formula for nth term as n minus 1 whole cubed. Now this sequence belongs to square numbers. If they were original square numbers, the formula would have been n squared. But since they're starting from 0, it's a backward shift. Therefore, we replace n with n minus 1. And we get the answer n minus 1 whole squared. This was simple for squares and cubes, but triangle numbers are different. In triangular numbers, n appears twice, so you must change both values of n. For example, if you decide to replace n with n plus 1, do it in both places, the first n and the second n. Okay, let's do an example. Write down the nth term of this sequence, 3, 6, 10, 15. First, we identify the family this sequence belongs to. It's not arithmetic sequence as difference is not same. These are triangular numbers whose original series is 1, 3, 6, 10. But they are not original triangular numbers as it does not start from 1. It is shifted forward as one term is skipped. Therefore, we will change both n's. Here, you have to be careful as many students make mistakes during replacement of both n to n plus 1. In the first bracket, instead of n, put n plus 1, in the second bracket 2. So it becomes 1 by 2 whole times n plus 1 whole multiplied by n plus 1 plus 1, which can be written as 1 by 2 whole times n plus 1 whole multiplied by n plus 2. Here, if you open up the brackets, it becomes the expanded form. Whereas in brackets, it's the simplified form. Just write like this. If you open them, you will just be wasting your time.
All right, write the nth term of the sequence 0, 1, 3, 6, 10. First question, is it arithmetic? No, because it's increasing by 1, then by 2, then by 3, so clearly these are triangular numbers. Now, if they were original triangle numbers, they should have started from 1, right? But here they start from 0, so it means we have a backward shift. Therefore, instead of n, we'll use n minus 1. Clear? So we'll take the nth term formula, which is 1 by 2 times n, whole multiplied by n plus 1, and replace both n's with n minus 1. It becomes 1 by 2 whole times n minus 1 whole multiplied by n minus 1 plus 1. It can be simplified to 1 by 2 whole times n minus 1 times n, or as some students prefer to rearrange it as shown. All right, now I want you to first revise it so that it gets memorized thoroughly. First, check if your sequence is arithmetic. If not, then it's either square, cube, or triangle numbers. Then check if it has a forward or backward shift issue. If it's still not that, then comes the next technique. This technique is normally not covered in textbooks, but clearly written in the syllabus. It's very important and most easy technique. Okay, if the sequence given is not from arithmetic, square, cube, or triangle numbers, then in such scenario, you make a table and include all the sequences of questions in the table. Then look for a vertical pattern. Yes, make a table including all the sequences in your question. The first row will always be 1, 2, 3, 4, 5, 6, up to n. This is the most basic arithmetic sequence, also known as term numbers. Okay, write 1, 2, 3, 4, 5, 6, and on left, write term number. And the nth term for these term numbers is n. Remember, the nth term of term sequence 1, 2, 3, 4, 5, 6 is n. All right, the first given sequence is 6, 9, 12, 15. As the difference is constant between two adjacent terms, therefore it is arithmetic sequence. We know that for an arithmetic sequence, the formula is Tn equals A plus n minus 1 times d. So here, A equals 6, d equals 3. Hence, Tn equals 6 plus n minus 1 multiplied by 3, which equals 3n plus 3. So we write the nth term for the second sequence. We note that the sequence was arithmetic. Okay, next sequence. Always ask, is the sequence arithmetic or not? As the difference between adjacent terms is not constant, therefore it's not. Now we recall the memorized sequences of square, cube, and triangle numbers. Here it matches the square series, 4, 9, 16, 25. So these are square numbers. As the sequence is starting from 4, therefore there is a shift and we replace n with n plus 1. The nth term is n plus 1 whole squared. Next, we got 8, 27, 64, 125. Let's predict the sequence. Yes, it's cube numbers, and it is also shifted forward by one term. So we will replace n with n plus 1, and the nth term formula is n plus 1 whole cubed. Now the next one. First question, is this arithmetic? No, it's also not square, cube, or triangle. Confusing, isn't it? Let's see if it's formed by subtraction, multiplication, or division of two sequences. And for that, we use vertical column method. At first it seems tricky, but after a few examples, you'll realize it's not. Here we have 3 as the first term. Just look in the column. What two numbers when added, subtracted, multiplied, or divided gives us 3? Let's test it. If we subtract 1 from 4, we get 3. Now let's verify from other columns. 9 minus 2 equals 7, 16 minus 3 equals 13, 25 minus 4 equals 21, and 36 minus 5 is 31. And 64 minus 6 is 58. Can you see the pattern? Sequence D is sequence B minus term sequence. At first, it's a bit hard to see, but with practice, you'll spot it easily. So for nth term, you'll do the same. Subtract the two nth term formulas. You'll get your answer. We get n plus 1 whole squared minus n. As you can see, we use vertical column method to derive the formula. For this, you must spot the vertical pattern and solve for the nth term formula. Okay? Don't confuse quadratic sequences with these sequences. That's a different thing. Quadratic sequences come after this. Once this method doesn't work, then we go to the quadratic sequence, not before. If you try to initially solve it with quadratic formula without checking the vertical method, then you will be solving a simple question with too much effort, which is not advisable. Now, let's try the next sequence. Here is a hint. If you see big numbers, this means it is the outcome of multiplication or addition of two numbers in the vertical column, right? Because when numbers suddenly get huge, it's either addition or multiplication happening. And here, it's clearly addition.
All right, let's check it out. 8 plus 1 equals 9. 27 plus 2 equals 29. 64 plus 3 equals 67. 125 plus 4 equals 129. 216 plus 5 equals 221. 343 plus 6 equals 349. See how easy it becomes once you know what to look for? Now, we will also do the same for nth term. We add n plus 1 whole cubed with n, and our formula for nth term will become n plus 1 whole cubed plus n. Now, look here. The next sequence is 4, 18, 48, 100, 180, 384. As they are not arithmetic, square, cube, or triangle numbers, so again we look for pattern in the vertical column. Clearly, multiplication is happening here. Our first term is 4. In the column above, we can figure it out. That is the outcome of 1 multiplied by 4. So we can say that the term sequence is multiplied with sequence B. Let's check the other terms of sequence F. 1 times 4 equals 4. 2 times 9 equals 18. 3 times 16 equals 48. 4 times 25 equals 100. 5 times 36 equals 180. And 6 times 64 equals 384. For nth term, we multiply n with n plus 1 whole squared, and we get n plus 1 whole squared multiplied by n. Okay, last sequence, 10, 29, 66, 127, 218, 343. A very basic mistake is that students jump directly to vertical pattern. You have to be careful. In exams, first check, is it arithmetic sequence? If not, then is it square, cube, or triangle numbers? All right, it's not arithmetic, square, cube, or triangle numbers. This is a special question. At times the sequence is easy, but we try to add, subtract, multiply, or divide two sequences in vertical pattern to find the sequence. But the examiner tricks us with a very simple question. It's so simple your brain is discarding it thinking it can't be that easy. But it is. Look at the whole table. Basically, this one is sequence C plus 2. The number 2 is added to the sequence C. See, 8 plus 2 equals 10, 27 plus 2 equals 29, 64 plus 2 equals 67, and 125 plus 2 equals 129. The question has tricked us in trying to merge two rows by looking for relationships, but sometimes you just need to add or multiply one whole row by a constant to make the next row. If you have understood the table, there are no other type of question that examiners can trick you with in vertical pattern questions. Okay, in the previous question, we had a full table, but sometimes the examiner doesn't give a table to trick you because to figure out a vertical pattern, you need a table. So now making the table becomes your job. If your question isn't arithmetic, square, cube, or triangle numbers, then you already know it's a vertical pattern question. And if the table isn't shown, you must make it. In that table, the first line of the table will always be term numbers, 1, 2, 3, 4, till n. Keep that in mind. Then add all the parts or sequences from the question below that. That's how you'll see the vertical pattern. Let me show you a past paper question to give you clarity.
Okay, first four terms of the sequence are 55, 53, 49, 41. The nth term is 57 minus 2 power n. The question is to find the fifth term. So, what should we substitute for n? Put n equals 5, and we get 57 minus 32. And the answer is 25, right? Fairly simple question where the nth term is given, and we're asked for fifth position. We just substituted n equals 5 and got the fifth term. All right, now, next question. Write down the nth term of 54, 51, 46, 37 sequence. Okay, first check if it's arithmetic. Well, it's not, as the difference in two adjacent terms is not the same. 51 minus 54 equals minus 3, 46 minus 51 equals minus 5, and 37 minus 46 equals minus 9. We also don't find square, cube, or triangle numbers, right? So this must be a vertical pattern question, and since no table is given, we'll make one. As I have already told you, to put the term sequence on the top inside the table, like this. Then we put the given sequence of 55, 53, 49, 41, along with its nth term, as it's already given, so we need not go into the hassle of solving for one. We put 57 minus 2 to the power n. Now we put the sequence for which we want to find the nth term, 54, 51, 46, 37. This is the interesting part. You have to focus. We will look vertically to find a relation for the sequence. If you look carefully, the third sequence is second sequence minus term sequence, right? So for nth term formula, we also do the same, and we get 57 minus 2 power n minus n. Perfect. This is the most easy and only way to find the answer to such questions. Remember it and give it some practice from past papers and other resources. All right. If you have got the concept of what we have studied, then more than 90% of the exam's questions can be solved using what we've learned. The only thing that is left is the small portion of quadratic or exponential sequences. Okay, now let's study quadratic sequences first. It's very less time-consuming and mostly memory-based. In order to recognize quadratic sequence, we will follow the same order. First, we check whether it's arithmetic or not. Then, whether it belongs to square, cube, or triangle numbers. Then, you check if there's a vertical pattern. If it doesn't fit in any of these three, then it belongs to the quadratic family. A word of caution, never start with quadratic directly because it will waste your time. It'll turn a 1-mark question into 4 marks of working. You must go in this order: arithmetic, then square, cube, or triangle numbers, then vertical pattern, and finally quadratic. Okay, now we will see how to identify a quadratic sequence. In arithmetic sequences, the first difference stays the same, but in quadratic sequences, the second difference stays the same. Let's see what that means. Look, by how much is it increasing from first to second term? It's plus 5. The difference between second and third term is plus 9. And third and fourth term difference is plus 13. This clearly shows it's not arithmetic. But we don't see square, cube, or triangle numbers pattern. Therefore, it does not belong to that families also. It's also not vertical, as it's the first part of the question, and we cannot make table, except that we have term sequence. Therefore, we will find the difference between the terms. Let's check what second difference is. The second difference is calculated by taking the difference of the first differences we have calculated, which is shown in blue. As we can see, 9 minus 5 equals 4, 13 minus 9 is also 4, and so on. So the second difference of the sequence is the same. This blue one is called the first difference, and the yellow one is the second difference. If the second difference comes out the same, it's quadratic sequence. Such numbers are called quadratic numbers, and their nth term is calculated as an squared plus bn plus c. Now the relationships are: the first difference is equal to 3a plus b. The second difference is equal to 2a. The first term is equal to a plus b plus c. Therefore, the bottom number is equal to 2a. The one above that equals 3a plus b, and the top one equals a plus b plus c. To find the values of a, b, and c, we always solve from bottom to top. First, the bottom. 2a equals 4. From that, can you find a? Of course, and the answer is 2. Then we use 3a plus b. Here we put the value of a and equate it to 5. By solving it, we get b equals -1. Finally, using a plus b plus c, we plug values of a and b, which we have just calculated, and equate it to 1 to find c. Here we got 2 minus 1 plus c equals 1. So c comes out to be 0. Since this is a quadratic sequence, therefore its nth term will be an squared plus bn plus c. We have the values of a, b, and c, and we write the nth term as 2n squared minus n. We don't write plus 0 as it has no effect. That's your final answer, but do remember, bottom term is 2a, middle term is 3a plus b, and top term is a plus b plus c. Got it? Perfect. So how do you recognize if it's quadratic? Of course, we look for second difference being constant. Okay, let's do another example. Step 1. Check if it is arithmetic. Let's check. From -2 to -1, the increment is 1. From -1 to 4, the difference is +5. From 4 to 13, it's +9. From 13 to 26, there is increase by 13. So, it's not arithmetic sequence. Now, the second difference. From 1 to 5, we have +4. From 5 to 9, it's again +4. And 9 to 13 is also +4. As the second difference is same, so it's quadratic. Now, to get the nth term, we take bottom number 4 equals 2a, middle number 1 equals 3a plus b, top number -2 equals a plus b plus c, and we'll solve from bottom to top. 2a equals 4, which gives us a equals 2, then 3a plus b equals 1. Here, by plugging a equals 2, we get 6 plus b equals 1, and finally, b equals -5. Next, a plus b plus c equals -2. We plug values of a and b, which gives us 2 minus 5 plus c equals -2, and finally, c equals 1. The nth term is equal to an squared plus bn plus c. We have a equals 2, b equals -5, c equals 1. So nth term equals 2n squared minus 5n plus 1. That's how you solve quadratic sequence. You just need to use the right order. If you apply it at the wrong time, like on square or cube numbers, it will completely mess up your answer. Let's take our previous example, 0, 1, 4, 9, 16, 25. As you can see, it is square numbers shifted to the left, and its nth term is calculated by replacing n with n minus 1, and we get n minus 1 whole squared. Now here is a very important point. The nth term n minus 1 whole squared means it is quadratic term, as if we expand it, we get n with highest power of n as 2. Therefore, it means that this sequence of square numbers can also be solved with quadratic method. Let me repeat. Square number's nth term has n with power of 2. Therefore, its nth term is quadratic in nature. So square sequence can also be solved with quadratic method. Let's give it a try. The first difference of the sequence is +1, +3, +5, +7, and +9. The second difference is throughout +2. Now we solve for a, b, and c. Here, 2a equals 2, where a comes out to be 1, then 3a plus b equals 1, and again by solving it, we get b equals minus 2, and from a plus b plus c equals 0, and putting the value of a and b, we get c equals 1. Eventually, they'll end up with n squared minus 2n plus 1, which is equivalent to n minus 1's whole squared. See, such a long process, and we end up with same answer. So one easy method was to identify square numbers and solve it in one step, or the difficult and time-consuming method is to solve it through quadratic method. There's no need to do all that hassle, it's just not worth the extra effort if you can do it the easy way. That's why you have to check the sequence for arithmetic, then for square, cube, or vertical method before going for quadratic method. Okay, now the last type of sequence is called exponential sequence. Exponent means power. Here is an example of exponential sequence. 2, 4, 8, 16. If you look closely, these are powers of 2. 2 raised to the power 1, 2 raised to the power 2, 2 raised to the power 3, 2 raised to the power 4. As the base 2 is not changing, we can say 2 is constant. Therefore, you already know that in the nth term, there will be 2 to the power of something. Now focus on the power part. We're observing an arithmetic sequence in the power. 1, 2, 3, 4. So our sequence is in the powers, not in the base. This means in exponential sequence, base is fixed and the sequence is in the powers. The nth term of the powers is n, as we have been using in term sequence, which is basically arithmetic. Therefore, nth term is 2n. Let's take another example. 1, 2, 4, 8, 16. You can write it as 2 power 1, 2 power 2, 2 power 3, but what is this? Remember, anything to the power of 0 is 1. So 1 can be written as 2 power 0. Now, in our sequence, 2 is constant, and its power will form an arithmetic sequence. 0, 1, 2, 3, 4. Can you figure out the nth term of the exponent? It is term sequence shifted backward, so we replace n with n minus 1. Now we have the nth term of the exponential sequence as 2 raised to the power n minus 1. Okay, this is how you solve exponential sequence. The base is fixed, and the powers follow a sequence. If you see numbers sequence like 2, 4, 8, 16, 32, you know it's exponential. To find the nth term, fix the base, check the power pattern, and apply it. At times, first term itself in the sequence may not make sense in exponential sequence. Start from wherever it makes sense, as in this sequence. We start from where it makes sense. 2 raised to the power of 1, then 2 raised to the power of 2, agreed, and so on? And we know that this is 2 to the power of 0, and this one is 2 to the power of minus 1. And what is this one? It's 2 to the power of minus 2, because what does 2 to the power of minus 2 mean? It's 1 over 2 to the power of 2, or 1 by 4. So my exponents are minus 2, minus 1, 0, 1, 2, 3. It is arithmetic sequence shifted 3 times to the left, therefore we replace n with n minus 3. Our nth term will be 2 power n minus 3. The key technique in such questions is to observe the pattern in the powers. The sequence that appears in the powers, that's the actual pattern we use. Now, sequences do need practice to get used to it. I'll give link to practice questions from past papers so that you'll start understanding sequence questions much better. This completes our sequences chapter. For patterns, you have to practice questions of past papers, as there's no theory to study for it. Okay, let's summarize it. There are 4 types of sequences in our syllabus. Number 1, arithmetic sequences. Number 2, square, cube, and triangular numbers and their shifts. Number 3, we'll check the vertical pattern, and if it doesn't fit all 3 types of sequences, then we'll move toward applying the quadratic formula. If you apply the quadratic formula without checking the vertical pattern, it won't be exactly wrong, but it'll take much longer. So it's not advised to do that. Do revise whatever you have learned, or else you'll forget it. Like and subscribe for more educational video lectures.